This video will demonstrate how to perform a structural simulation on an assembly in 3DEXPERIENCE. We will track our progress using the assembly workflow diagram. We use the same trailer hitch model used in the previous videos. To remind you, the trailer hitch is supposed to support a hitch load of 2,500 newtons and a pull load of 26 kilonewtons. For this model, we only simulate the adjustment bar, lug, and lock pin. First, we will define the simulation model for the assembly. We have already created finite element models for the individual components. So, creating the assembly model will be quite easy. We start by inserting a representation into the hitch sub-assembly. We select a finite element representation. Notice, this is created at the same level in the model tree as the parts. Double-clicking on the finite element model loads the structural model creation app and allows us to select the abstraction shapes we will use in the simulation. Next, we click on Setup on the action bar and select the contributing finite element models. We are going to exclude the second pin from our simulation. Clicking on Update associates the finite element models created on the parts to the new assembly model. In reality, a safety clip prevents the pin from sliding out of the hole. Instead of modeling the clip, we are going to create a soft spring connection between the end of the pin and the side of the lug. We hide the mesh so we can better see the geometry. Then, we select Connections from the action bar and select a spring connector. The spring spans between the two selected faces. We enter a spring stiffness of 100 and click OK. After we click Update, you can see the connector has been added to the model. We define geometric groups of element faces, where contact will occur between the parts. This will make it easier to define surface-based contact pairs. The groups are defined under the assembly mesh. We are now ready to start defining the simulation scenario. We launch the Mechanical Scenario app. This app should be your first choice for modeling multiple parts with contact. We select Structural and click OK. From the action bar, we define the finite element model. It is a good idea to verify the model is correct. Next, we need to define the procedure. Due to the complex contact and initial clearances between parts, we will use an implicit dynamic step for our solution method. 100 increments may not be enough, so we enter 1000. We want a quasi-static result. An initial time increment of 0.001 should be adequate. We set the minimum increment size to 1e-8. And enable unsymmetric storage. We are now ready to select the element type. To reduce the solution time, we change the element type to C3D10. We need to make sure we use surface-to-surface contact with these elements. Now, we can define the contact. We start by defining the contact properties. In the tangential direction, we define a friction coefficient of 0.1. We also specify the penalty method, in the normal direction. Because we want to output the contact forces, we will define surface-based contact, instead of using general contact. We select the groups, our contact property, and verify the surface-to-surface method is used. We define the other 4 contact pairs in the model, and we now have a lot of information that needs to be updated. For this app, updates are done using the model and scenario check. We can now define the restraints. We will fully restrain the adjustment bar, but we will not specify any restraints on the lock pin or the lug. The contact and frictional forces will prevent the motion of these 2 components. We hide the mesh so we can more easily select the geometry. On the back pinhole, we restrain motion in the X and Y directions. Now, we need to restrain the Z direction. Using the selection filter makes it easier to select the edges. We select the 2 edges that will contact the hitch receiver and restrain them in the Z direction. Now, we can define the loads. We can use the same technique we used when we analyzed just the lug component. We apply a remote force using the same published geometry. However, this time we are going to first apply the hitch load. Then, in a second step, we will apply the pull load. This loading sequence is more like what is seen in the real-world application. Before defining the pull load, we need to define a second implicit dynamic step. We use the same parameters for this step as we used for the first step. Now, we can define the 26 kN pull load. Before running the simulation, we need to request output of the contact forces. We changed the names of the steps, so they are more meaningful. Notice, step 2 is the active step. We want to output data for both steps, so we need to make step 1 the active step. We will create an output request for the contact forces between the front of the adjustment bar and lug. For support, we select Sim feature. Then we select the contact pair associated with those surfaces. This will be history output. We select the contact forces due to contact pressure and click on OK. We defined all the other history output requests. Nonlinear simulations like this can generate large amounts of data, so we will also edit the field output. Field output will be generated every 10 increments. Our model is elastic, so we disable these. We also disable acceleration. We enable contact status, in case we need it to diagnose convergence problems. We update the model, and then save it. We expect this model to generate a fairly large results file. So, we are going to store the results locally. We are now ready to perform a simulation check. We specify length, in millimeters, and select 4 cores. After a few minutes, we have the results. We review the warning messages, and see nothing to cause concern. Before submitting the model to be solved, we will show you how to leverage the simulation check to verify the initial state of your model. We double-click on the results. Then, we create a contour plot of the contact opening. Let's create a display group of just the lug. If you had initial interference, you would immediately see that. Now, we run the simulation. This simulation will take a couple of hours. However, we will look at key points as the solution progresses. At our first check, we see a warning message about contact, and the displacement being too big. If we look at the Iterations tab, we can see that we completed the first 3 increments, without any severe discontinuity iterations. We are likely just starting to establish contact. A short time later, we see a new warning about elements distorting excessively, and convergence is judged unlikely. This time when we check the Iterations tab, we see no increment has been successfully completed with a severe discontinuity iteration, and the solver is cutting down the time increment. This is normal behavior when contact is first being established. The model has been running for quite some time now, and it has actually completed the first step. If we look at the increment size, we can see that once the contact became well established, the increment size started increasing quite quickly. Again, this is normal behavior for a simulation like this. After a couple of hours, we see that the solver is done. Now, we can do a brief review of the results. Let's start with the contact opening. The maximum penetration is about 1/10 of the smallest manufacturing tolerance. We may need to scale the penalty stiffness to reduce the penetration. Next, we look at the von Mises stress plot. The stress is significantly lower than the result we obtained when we modeled just the lug. However, if we apply a factor of safety of 8, which might be typical for a cyclic load, we see that the part design is inadequate. After editing the display group, we can see that the stress in the adjustment bar is also too high. We can create a XY plot of the contact force output. This will help us understand how the loads are being transmitted through the model. This knowledge may help us to modify our design. The local results are stored in this user directory. The names are masked. However, from the timestamp, we can see the results file for this model is over 300 megabytes. Before saving results from nonlinear models to the cloud, you should check with your instructor.